What if I told you that the greatest weapon of the Roman Empire was not the famous short sword, but an ordinary shovel? Rome's success, its ability to conquer and hold vast territories, was based not only on the discipline of its legions, but also on engineering genius that was thousands of years ahead of its time. We admire their armies, but we often forget that each legionnaire was not only a warrior, but also a highly skilled builder, capable of erecting fortresses, bridges, and siege engines. This is the forgotten science of military engineering, where ballistas were more accurate than sniper rifles, and siege towers were multi-story moving fortresses. Watch the video to the end, and you will learn how the Romans built bridges across impassable rivers in just 10 days, and why their siege technology still amazes modern engineers. I will reveal the most closely guarded secret of the Roman army. Its invincibility lay not in its weapons, but in its tools. A Roman legionnaire was not just a soldier, he was an engineer, surveyor, and builder who had undergone rigorous training. Each warrior carried not only armor and a sword, but also a heavy set of tools known as Maria's mules, which included a pickaxe, delabra, a shovel, a basket for carrying earth, and a saw. These tools were as standard equipment as a shield, and they were used almost more often than a sword. It was this ability to work collectively and in an organized manner that gave Rome a decisive advantage over any opponent. While their enemies relied on fury and bravery in one decisive battle, the Romans relied on methodical preparation and engineering calculations. They turned the terrain itself into their ally, changing the landscape at will. If they needed to cross a river, they built a bridge. If they needed to take a city, they erected siege engines that towered above the city walls themselves. This army did not simply fight, it built its way to victory, leaving behind not only defeated enemies, but also roads, fortresses, and aqueducts. The training of a legionnaire was comprehensive and incredibly difficult, tempering his body and spirit for any challenge. Recruits not only learned to march and fight in formation, but also spent hours digging trenches, felling trees, and building mock fortifications. Discipline was absolute, and any order, whether it was to attack the enemy or build a camp, was carried out with equal precision and speed. Commanders understood that a soldier who was tired and exhausted by army labor was more resilient and obedient in battle than one who knew only the art of sword fighting. This dual status of soldier builder was unique in the ancient world and amazed their opponents. Barbarian tribes, when confronted with legions, often could not understand who they were dealing with, warriors or a team of builders. They saw how, in a matter of hours, an impregnable fortress surrounded by a moat and a rampart grew out of nowhere. This speed and organization demoralized the enemy even before the battle began, instilling in them the idea that they were facing some kind of supernatural force. The most striking symbol of this engineering power was the delabra, a universal pickaxe hoe. It was not just a tool for digging the ground, but also a formidable weapon in close combat if a legionnaire lost his sword. The delabra was perfectly balanced for cutting roots, splitting stones, and piercing enemy shields or helmets. It was so important that its image was often engraved on the tombstones of legionnaires as a symbol of their dual profession and pride in their work. The legion's ability to quickly erect fortifications, or castra, was a tactical advantage that cannot be overestimated. Every evening, even after a long and tiring march, the army would set up a fully fortified camp. Thousands of people worked as a single mechanism, and in just 3 to 4 hours, a rectangle of walls appeared in the open field, protected by a deep moat and a palisade. This gave the soldiers a safe rest and made sudden night attacks by the enemy impossible. It was this approach, combining military discipline with engineering genius, that allowed Rome to become the ruler of the world. Each legionnaire was a cog in this huge machine, but a cog that could both fight and create. Do you agree with this? Please tell us what you think about this and what trait of the legionnaires impresses you the most. Every opinion is valuable. And don't forget to subscribe to our channel so you don't miss out on new amazing facts from history. Are you ready to learn the truth about what still lies beneath our feet and connects continents? The famous phrase, "all roads lead to Rome," is not just a metaphor, but a literal description of engineering reality. The Romans were the first to understand that an empire depends on logistics, and logistics depends on roads. They created an extensive network of high-quality, paved highways with a total length of more than 400,000 kilometers, of which more than 80,000 were paved. This network connected the farthest corners of the empire, from Britain to Mesopotamia. The construction of a road, or via, was a complex and laborious process that had not changed much over the millennia. Roman engineers did not compromise on quality because the roads were built primarily for military purposes. They had to withstand the weight of marching legions, heavy wagons, and siege equipment in all weather conditions. Therefore, a Roman road was not just a path, but a multi-layered engineering structure designed to last for centuries. The process began with the work of surveyors, who used an instrument called a groma to plot the straightest possible route. The Romans did not like curves and preferred to cut through hills and drain swamps, but keep a straight line. Then the legionnaires dug a trench, or fossa, up to 1.5 meters deep. This foundation was key to the road's durability, providing drainage and stability. The first layer, the statumen, was laid at the bottom of the trench. Large, roughly hewn stones held together with clay or mortar. This layer served as the foundation and drainage system. On top of it went the rudus, a thicker layer of crushed stone, broken brick, and lime, which was carefully compacted. This layer provided strength and distributed the load, preventing the road from sinking. The third layer, the nucleus, or core, consisted of fine gravel mixed with lime and sand, which was essentially an early form of concrete. This layer was dense and waterproof and was carefully leveled. Finally, the top layer, the summa crusta or pavimentum, consisted of large stone slabs that were tightly fitted together. These slabs were given a slightly convex shape so that rainwater would run off into drainage ditches on either side of the road. An entire infrastructure was created along the roads to make travel fast and safe. Milestones miliarium were placed at regular intervals, indicating the distance to the nearest town or to Rome itself. Stations, mutationes, were built for changing horses, and inns, mansiones, for officials to spend the night and rest. This system, known as the cursus publicus, was the imperial postal and transport service, allowing messages to be delivered and officials to be transported at incredible speed. What modern infrastructure project, whether the internet or a global transport network, do you think can compare to the Roman road network in terms of its impact on civilization? But what if a wide and turbulent river stood in the way of this perfectly straight road? In the next chapter, we will learn how the Romans solved this problem with engineering audacity. What I am about to tell you may seem like fiction, but it is a documented fact that has amazed engineers and historians alike. In 55 BC, Julius Caesar faced a tactical problem. Germanic tribes were raiding Gaul and then quickly retreating across the Rhine, using the river as an impenetrable barrier. Caesar decided that for the safety of Gaul, it was necessary to show the Germans that the Rhine was no obstacle to the Roman army. But he rejected the simple and obvious solution, ferrying troops across in boats, considering it unworthy of the greatness of Rome. He made a decision that his contemporaries considered insane, to build a permanent bridge across the wide, fast-flowing, and deep river. This project was not so much a military necessity as an act of psychological influence, a demonstration of Rome's engineering superiority. Caesar wanted to prove that Roman genius and willpower could conquer nature itself. He described the entire process in detail in his Commentaries on the Gallic War, and this description is still used as a textbook on military engineering. The task was enormously difficult. At that point, the Rhine was almost half a kilometer wide, with a fast current and considerable depth. It was impossible to build a conventional bridge on supports. Under Caesar's personal supervision, Roman engineers developed a unique design based on inclined piles that were not simply driven into the bottom, but worked like a complex truss, where the pressure of the water only compressed and strengthened the entire structure. Construction began with the manufacture of huge logs sharpened at the end. These piles were knocked together in pairs on the shore, and then with the help of special rafts and mechanisms, copros, they were installed in the river. Each pair of piles was driven at an angle to each other, forming a V-shaped support. It is important to note that the piles facing the current were tilted against it. while those below were tilted with the current. This created an incredibly strong structure. At the top, these slanted pairs of piles were connected by a massive crossbeam, which was secured with special clamps. This fastened the support into a single unit. Then longitudinal logs were laid on these crossbeams, which served as the basis for the road deck. The decking, in turn, was covered with brushwood and compacted earth, so that not only infantry but also heavy cavalry could cross the bridge. To protect the bridge from logs or boats that the Germans could float downstream to destroy the supports, Caesar ordered additional protective piles to be installed upstream. They acted as breakwaters, taking the initial impact and protecting the main structure. It was a well-thought-out and comprehensive engineering system where no detail was overlooked. The most striking thing about this project is the timing. Thousands of legionnaires working around the clock as a single mechanism completed the construction of this gigantic bridge in just 10 days. One can only imagine the shock and awe of the Germanic tribes who saw the Romans literally shackle the sacred river before their eyes. It was a miracle beyond their comprehension. Caesar led his army across the bridge, carried out several demonstrations on the Germanic shore, showing that there were now no obstacles for him, and stayed there for 18 days. He achieved his goal. The Germans were demoralized and stopped their raids for a long time. Having achieved the desired psychological effect, Caesar returned to Gaul and ordered the bridge to be destroyed behind him. He proved that he could build it anywhere and anytime. This bridge was unparalleled in the ancient world and went down in history as a symbol of Roman engineering audacity. It was a project where engineering became an extension of military strategy. It showed that there were no impossible tasks for Roman legionaries, whether on the battlefield or on the construction site. They were capable of solving the most complex technical problems in the shortest possible time. The story of the bridge over the Rhine is a striking example of how the Romans used engineering not only as a tool, but also as a weapon of psychological warfare. They built not just to move around, but to inspire awe. If you enjoyed this incredible story of ingenious engineering and strategic thinking, please like this video so we know you are interested in such detailed analyses. What if I showed you a city that could be built in one evening and then dismantled and carried away the next morning? This is not science fiction, but everyday reality for the Roman legion, which was called a castrum, a fortified military camp. No other army in history paid so much attention to the security of its camp. For the Romans, it was not just a place to sleep, but the basis of their tactics, a symbol of order and discipline. Every legionnaire knew that after a long march, he would not be resting, but would have several hours of hard work ahead of him to set up camp. The uniqueness of the Roman castrum lay in its absolute standardization. Regardless of where the legion was located, in foggy Britain, in the forests of Germany, or in the deserts of Syria, the camp always had the same rectangular shape and identical internal layout. This was an ingenious solution that offered enormous advantages. Every soldier, even those arriving from other legions, knew exactly where the centurion's tent was, where the weapons depots were, and where the hospital was. This eliminated any confusion. The construction process was honed to perfection and was astonishingly fast. As soon as the army stopped for the night, surveyors, grammatiki, were sent ahead. They chose a suitable location, usually on a hillside near a water source, and used their grammata to mark out a perfect rectangle on the ground. They marked the location for the commander's tent, Praetorium, and the two main intersecting streets, Via Principalis and Via Praetoria. Immediately after that, thousands of legionnaires set to work, each knowing his maneuver. One group of soldiers dug a moat, fossa, around the entire perimeter of the camp. The depth and width of the ditch depended on the expected threat, but it was always a serious obstacle. The soldiers did not simply throw away the earth from the ditch, but used it to build an internal rampart, agger. This was the first line of defense. A wall or palisade, vallum, was immediately erected on top of this earthen rampart. To do this, each legionnaire carried 2 or 3 pointed stakes, sudes. These stakes were driven into the ground so tightly that they formed an almost continuous wall that was very difficult to overcome. All this work, digging the ditch, building the rampart, and installing the palisade, took an experienced legion only a few hours. Inside the camp, the same strict order prevailed. The legionnaires' tents, contubernium, each of which housed 8 people, stood in neat rows, forming streets. There were clearly defined areas for the infirmary, smithy, food stores, horea, and meeting places. This standardization was not only convenient, but also had enormous hygienic significance, helping to avoid the diseases that plagued other armies. Thus, the castrum was not just a camp, but a microcosm of Roman society. It was orderly, disciplined, standardized, and incredibly efficient. It was the legionnaire's home on the march and his main stronghold. Can you imagine a modern army capable of erecting temporary fortifications every evening with the same speed and efficiency? In the next chapter, we will see how these temporary camps and fortifications on the borders became the most grandiose defensive structures in human history. When the Roman Empire reached its maximum size under Emperor Trajan, the next task was not expansion, but the retention and defense of the conquered territories. This new defensive doctrine gave rise to some of the most impressive engineering projects in history. Instead of relying solely on mobile legions, the Romans decided to physically separate their civilization from the barbarian world. Thus was born the Lime system of fortified borders, crowned by the famous Hadrian's Wall in Britain. Built in 120 AD, Hadrian's Wall was not just a wall, it was a complex multi-level defensive system stretching 117 kilometers from coast to coast, cutting off the northern part of the island. Emperor Hadrian, who visited Britain, personally gave the order for its construction, and it was a project of colossal scale. Its purpose was not so much to stop invasions as to control the movement of people, collect taxes, and serve as a visible symbol of Roman power. The construction was carried out by 3 legions stationed in Britain. Thousands of soldier engineers worked for years to erect this structure. In its eastern part, the wall was built of stone, about 3 meters wide and estimated to be 5 to 6 meters high. In the western, more marshy part, it was originally built of peat and wood, but was later rebuilt in stone. It was a titanic task that required incredible logistical efforts. But the wall itself was only one element of the system. Along its entire length, small forts, or mile castles, were built every Roman mile, about 180 meters. They served as gateways through which controlled passage from north to south was possible, and as garrison posts. Between each pair of mile castles were 2 signal towers, turrets, which provided surveillance of the surrounding area and rapid communication along the entire wall. Directly in front of the wall on the north side, a deep V-shaped ditch was dug, and on the south imperial side, there was another ditch known as the vallum, not to be confused with the wall itself. The vallum was a huge trench with 2 earthen ramparts on either side and probably served to demarcate the military zone and prevent unauthorized access from the south. The entire system was a living, breathing organism, not a dead barrier. The garrison of Hadrian's Wall consisted not of legionaries, but of auxiliary troops, or auxiliaries, recruited from various parts of the empire. They lived in the 16 large forts built along the wall, such as Housesteads and Windolanda. These forts were fully fledged military bases with their own headquarters, barracks, hospitals, granaries, and even baths. Life here was harsh but organized, and archaeological finds, such as the famous Windolanda tablets, give us a unique insight into the daily life of the frontier troops. Are you ready for the shocking truth about how accurate and powerful ancient artillery was? When the Roman army approached the walls of an enemy city, a completely different war began, a war of engineering. The Romans brought the art of siege warfare, or poliorketics, to frightening perfection. They rarely relied on a simple assault, preferring a methodical, engineered siege that guaranteed results. Their artillery played a key role in this, which was not just a throwing machine, but a high-precision mechanism. The main secret of Roman artillery was not the sling or catapult as we understand it today, but the torsion engine. The Greeks invented this principle, but the Romans perfected and standardized it. Instead of the elasticity of wood, as in the medieval trebuchet, these machines used the incredible energy stored in twisted ropes made of animal tendons or horsehair. These bundles of tendons, placed in sturdy frames, could store and release enormous amounts of energy, acting like giant springs. The most common machine was the ballista. It was essentially a two-armed machine, similar to a giant crossbow but operating on the torsion principle. It had two arms inserted into separate bundles of twisted tendons. Ballistas were incredibly accurate and could throw both heavy stones to destroy walls and large arrows, bolts, to strike defenders on the walls. The Romans built ballistas of various sizes, from small ones mounted on carts to giant stationary guns. For more accurate sniper work, the Scorpion was used. It was, in essence, a smaller version of a ballista, optimized for throwing long, heavy arrows. The Scorpion was valued for its accuracy at long distances. A legion armed with a battery of several dozen Scorpions could completely clear enemy walls of defenders, creating a dead zone and allowing assault groups to approach the walls. Julius Caesar highly valued these machines and actively used them in Gaul. If the ballista was a crossbow, then the onager, or wild ass, was a real catapult. It was a single-shouldered torsion machine. It had one massive lever that passed through a horizontal bundle of twisted tendons. At the end of the lever was a spoon or sling for the projectile. When released, the lever flew upward with tremendous force and struck a special crossbar, throwing the projectile along a high trajectory. Onagers were used to throw huge stones and barrels of flammable mixture to destroy the roofs of buildings and cause panic in a besieged city. The manufacture of these machines was a complex process requiring precise calculations and high-quality materials. The main value was tendons, which had to be carefully soaked and prepared. Tensioning mechanisms known as winches and gates allowed for precise adjustment of the twisting force, which directly affected the range and power of the shot. Each legion had its own artillery park, artilleria, and a team of specialists, ballistari, to maintain it. The use of artillery was not chaotic, but tactically thought out. Before the assault began, the Romans deployed their machines on specially prepared and fortified platforms. They began methodical shelling, concentrating their fire on the most vulnerable parts of the wall, such as gates or towers. The goal was not only to breach the wall, but also to break the will of the defenders, preventing them from raising their heads. The accuracy of these machines was remarkable. There is evidence that an experienced ballista crew could hit a single target on the wall from a great distance. This was not just stone throwing, but a real artillery duel in which the Romans, thanks to their standardization and engineering training, almost always emerged victorious. Their machines were more reliable, powerful, and accurate than anything their enemies could oppose them with. This artillery was so effective that it was used not only in sieges, but also in field battles. Small Scorpions mounted on carts, carroballistas, could follow the infantry, providing them with fire support. They acted as an early form of field artillery, raining arrows down on enemy ranks even before the legions engaged in close combat. Roman artillery represents the pinnacle of pre-industrial engineering in the field of weaponry. It combined complexity of design, understanding of physics, albeit empirical, and tactical flexibility. What do you think was more difficult, building and maintaining such a complex torsion machine, or learning to aim it accurately and hit the target? But what if the walls were too thick and the defenders did not surrender even under a hail of stones? In the next chapter, we will learn how the Romans approached the walls closely with the help of real land ships. When the artillery suppressed the defenders and cleared the way, heavy siege equipment came into play. The Romans understood that the main challenge was the height and strength of the walls. To solve this problem, they built real engineering monsters on site, the most impressive of which was the siege tower, or turris. This was not just a ladder, but a multi-story mobile fortress, often taller than the walls it was designed to storm. The construction of a siege tower was a massive project that could take weeks. It was assembled from massive wooden beams right in front of the besieged, which in itself was an act of psychological intimidation. The tower had a wide base and narrowed towards the top for stability. Inside, it was divided into several floors connected by staircases. Each floor had its own purpose and was filled with soldiers. This colossus moved on huge wooden wheels or rollers. In order for the tower to approach the wall, the legionnaires first had to carry out a huge amount of preparatory work. They filled in the moat and built a special ramp, or agger, a sloping embankment of earth, stones, and logs that led directly to the wall. This ramp was carefully compacted to withstand the weight of the multi-ton structure. The greatest threat to the wooden tower was fire. The city's defenders desperately threw burning arrows and barrels of resin at it. To counter this, Roman engineers used a multi-level defense system. The tower was covered with iron sheets, or more often, freshly skinned animal hides. These hides were wet and prevented the wood from catching fire. In addition, there were always soldiers on the tower with supplies of water and vinegar to extinguish fires. The lower floors of the tower often housed another terrifying mechanism, a battering ram, or Ares. It was a huge log, often shackled at the end with iron in the shape of a ram's head. The battering ram was suspended by chains or ropes inside a covered gallery, which allowed soldiers to swing it with great force without having to exert themselves to keep it suspended. This covered gallery, or tortoise, testudo, protected soldiers from stones and arrows flying from the walls. The upper floor of the tower was the main assault platform. It was level with or even higher than the city wall, giving Roman soldiers a tactical advantage. From this floor, archers and scorpions could fire accurately at the defenders, clearing the way for themselves. When the tower got close, a special bridge, or exostra, was thrown from the top floor, and the legionnaires rushed to the wall, engaging in battle. The entire structure was not just a pile of wood, but a complex mechanism. Inside the tower were not only assault troops, but also artillery. Small ballistas or scorpions could be installed on the middle floors, firing through special loopholes and suppressing resistance on the walls as the tower approached. It was a truly multifunctional weapon. But what if the walls were too high for towers and too thick for battering rams? Roman engineers had an answer to this challenge as well. They took the war from the surface underground, using the ancient and terrifying art of cuniculus, or tunneling. This tactic was slow, dangerous, and required iron endurance, but its results were devastating. Roman sappers, or cunicularii, were specialists in this invisible warfare. There were two main types of military tunneling. The first, simpler type, was designed to sneak under the wall and emerge inside the city. Such a tunnel was dug from a remote and hidden place, often at night, to conceal the excavation. It was an extremely difficult task, requiring precise calculations to emerge in the right place. But if successful, it allowed the gates to be opened from the inside and the army to be let in. The second and more common type of undermining was aimed at collapsing the walls. This was the pinnacle of engineering. Engineers began digging a tunnel at a safe distance from the walls, often using special protective shelters for cover. The tunnel ran at an angle downwards and then horizontally until it reached the foundation of the city wall. It was hard and dangerous work in cramped, dark conditions with a lack of oxygen. Once they reached the foundation, the sappers began to widen the tunnel, creating an entire chamber under the wall. As they excavated the soil, they installed powerful wooden supports, posts, and beams to prevent the wall from collapsing prematurely and burying them alive. This work required not only courage, but also a deep understanding of how weight is distributed and the pressure exerted by multi-ton stone masonry. When the chamber under the wall was ready and tightly packed with wooden supports, the most critical phase began. The sappers brought a huge amount of combustible materials into the chamber: dry firewood, brushwood, resin, sulfur. They stacked all this around the wooden posts that held up the wall. Once everything was ready, the tunnel was set on fire. The fire, burning in a confined space, consumed the wooden supports. As the posts burned through and turned to ash, they could no longer support the weight of the wall. Without support, a huge section of the foundation sank into the void, and the entire wall above this spot collapsed with a deafening roar, forming a wide breach. Assault troops immediately rushed into this breach. The defenders of the cities, of course, knew about this threat and tried to counter it. This is how the art of counter-undermining was born. The besieged placed vessels with water or bronze basins with peas around the entire perimeter of the walls. The vibration of the earth from underground work caused ripples on the water or made the peas tremble, indicating where the enemy was digging. In this case, the defenders began to dig a counter-tunnel. When the two tunnels met, real battles took place underground. In narrow, dark passages where it was impossible to swing a sword, soldiers fought in horrific conditions. Often, countersappers simply broke through into the enemy's tunnel and released suffocating smoke from wet straw and sulfur to smoke out or neutralize the Roman diggers. Julius Caesar describes the sapper warfare during the siege of Avaric in Gaul in detail in his memoirs. The Gauls proved to be skilled miners and constantly carried out counter-tunneling, trying to set fire to the Roman siege rampart from underground. It was a titanic battle of engineering minds, which Caesar ultimately won thanks to the perseverance and discipline of his legionary engineers. The art of undermining was a secret weapon of the Roman army. It required patience, composure, and high technical skill. It was dirty, slow, and thankless work, far from the glory of open combat. But it was precisely this work that often led to the fall of the most impregnable fortresses, proving that, for Roman engineers, there were no obstacles either on land or underground. Roman engineering genius was not limited to construction and destruction. One of its greatest achievements was the conquest of an element that was valued above gold: water. The Romans' mastery of hydraulics and water flow management was absolute and served both civil and military purposes. They understood that water was life, but also a powerful tool that could be used to their advantage. The most famous manifestation of this skill was, of course, the aqueducts. These grandiose structures, spanning valleys and piercing mountains, were not just pipes, but symbols of Roman civilization. They carried clean water to cities, supplying baths, fountains, and private homes. But they were also vital to the army. A permanent military camp, not to mention an entire legion, consumed enormous amounts of water, and aqueducts provided for this need. The engineering precision required to build an aqueduct is astonishing. Roman engineers had to calculate the slope with incredible accuracy, just a few centimeters per kilometer. This constant, barely noticeable slope ensured the smooth flow of water under the force of gravity for tens of kilometers. They used sophisticated leveling instruments, such as the courbat, to maintain this gradient. But water was also used more aggressively in warfare. When besieging a city, one of the first steps taken by the Roman army was to locate and cut off the enemy's water sources. They either poisoned wells or, more sophisticatedly, found and destroyed underground water pipes or aqueducts leading to the city. Deprived of water, the city could not resist for long, and this was a bloodless way to force it to surrender. Sometimes the Romans used the opposite tactic. If the city was located in a low-lying area, they could build dams and embankments to flood it, or at least make the approaches to the walls impassable swamps. They diverted river channels to dry up moats, or conversely, to direct the flow to wash away the foundations of the walls. This hydraulic warfare required a deep understanding of the landscape and fluid mechanics. Perhaps the most impressive example of the use of hydraulics on an industrial scale was Roman gold mining in Spain, for example. At the Las Medullas mines, engineers built a complex network of aqueducts that brought water from mountain rivers to the deposit. Then they used a method known as hushing. Water was stored in huge reservoirs and then suddenly released. The powerful flow of water literally washed away entire mountain slopes, exposing gold-bearing layers. Although this was not a direct military application, the technology and scale of this project demonstrate what Roman engineers were capable of. They could move not only earth, but entire mountains using the power of water. These same skills were undoubtedly applied in military affairs, for example, to quickly destroy earthen ramparts or wash away enemy siege embankments. Water management was also key to construction in difficult conditions. The Romans invented opus cementitium, or Roman concrete, which could set underwater. This allowed them to build bridges with strong supports directly in the beds of turbulent rivers and to erect massive port structures and piers that could withstand the onslaught of the sea. This technology gave them control over rivers and coastlines, which was critical for logistics and troop movements. Roman engineers were true masters of water. They learned how to find it, transport it over vast distances, use its energy for work, and harness its power for destruction. This ability to control the most important element was another component of their total superiority, allowing them to build a civilization and wage wars with an efficiency unmatched by anyone else in the ancient world. Why? After 2,000 years, can we still walk across Roman bridges and marvel at the dome of the Pantheon? The answer lies in two key inventions that became the eternal legacy of Roman engineering: Roman concrete and the arch. It was the combination of these two elements that allowed the Romans to move from simple construction to true architecture. and create structures that defied time itself. Roman concrete, or opus caementitium, was a real revolution in construction. Unlike the simple lime mortar used before them, the Romans created hydraulic concrete. They empirically discovered that mixing lime with volcanic ash, which they called pozzolana, after the city of Pozzuoli, produced an incredibly strong and, most importantly, water-resistant material. This concrete could even set underwater, which made it possible to build ports, bridges, and aqueducts. This material was not only strong, but also versatile. Concrete could be poured into any shape, allowing for the creation of complex structures such as arches and domes, which would have been impossible using only stone. It was cheaper and required less skilled labor compared to masonry. Legionnaires could quickly build strong fortifications, foundations, and walls that could withstand the test of time and battering rams. The second pillar of Roman engineering was the arch. Although the arch was known before the Romans, they were the first to understand its true potential and perfect its use. The arch is a brilliantly simple solution that allows vertical loads, weight, to be redirected into horizontal thrust on the side supports. This allowed the Romans to span huge distances that would have been unthinkable using a simple beam system. The Romans did not stop at a simple semicircular arch. They developed this idea by creating cylindrical vaults, essentially an elongated arch, to span tunnels and buildings. They learned to intersect two vaults, creating a cross vault that allowed for even more efficient load distribution. The pinnacle of this development was the dome, an arch rotating around its axis, which allowed them to create the largest unreinforced dome space in the world in the Pantheon, which was unsurpassed for more than 1,500 years. The combination of concrete and arches was a recipe for eternity. Aqueducts, such as the famous Pont de Gare in France, are multi-tiered arcades that combined elegance and incredible strength. They carried water, but were also symbols of power. The Colosseum is essentially a structure of concrete vaults and arches that could accommodate tens of thousands of spectators. Military engineering also benefited from these innovations. Fortress walls became thicker and stronger thanks to a concrete core faced with stone. Gates and towers were reinforced with arch structures. The bridges built by the legions were no longer temporary wooden structures, but became monumental stone structures capable of serving for centuries and ensuring the rapid transfer of troops at any time of the year. This legacy is not just the ruins we see today. It is a set of principles: standardization, modularity, the use of quality materials, and a deep understanding of mechanics. Modern engineers designing bridges, tunnels, and stadiums still use the same basic principles of load distribution that were perfected by Roman legionary builders. That is why, when we talk about the fall of Rome, we must remember that its engineering genius did not fall with it. It became the foundation of all Western civilization. From the roads we drive on to the principles of building our homes, we still live in a world that was largely designed and built by engineers in sandals and tunics. Their science has not been forgotten. It has simply become part of our foundation. We have taken a journey into a world where soldiers were engineers and a shovel was valued no less than a sword. Roman military engineering was not just a set of skills, but a whole philosophy. It was a combination of iron discipline, standardization, incredible ingenuity, and the will to conquer not only peoples, but nature itself. From the roads that connected the continent to the machines that crushed walls and the aqueducts that carried life, the handiwork of Roman genius is evident in everything. It was this engineering approach, and not just military prowess, that allowed a small republic on the Tiber to become one of the greatest empires in human history. They built for the ages, and their legacy still surrounds us today, reminding us of what civilization can achieve when it has the will, order, and knowledge. What do you think of these incredible engineering achievements? Which one, whether it's Caesar's bridge, artillery, or the art of sappers, did you find most impressive? Suggest topics for future videos you'd like to see on our channel in the comments. And don't forget to subscribe so you don't miss out on new explorations of the mysteries of the past.